In this lesson, we will talk more about properties of functions, including domain, range, but also some other properties like zero of a function and the behavior of a function. For example, if the function is decreasing, increasing, it has a maximum, minimum. Let's recall what's a domain. Domain is the set of all input values that can be used to evaluate the function. So if we can take an x, plug it into the formula of a function, and be able to assign a value to it, such a point belongs to domain. If you have any graph of a function, the domain is the projection of this graph onto the x-axis. So in this example is the set marked by purple. Range is the set of all output values of the function. So what kind of values can we obtain? In this particular example of a parabola, the possible values starts from -1, and then we can obtain any other value higher than 1. So similarly as before, we project the graph, but we project it onto y-axis. And on this example, the range is marked in green. Another important property of a function is zero of a function, which gives us the idea where the function crosses the x-axis. So zeros of this particular function are 1 and 3. Generally, a zero of a function is any value from the domain of the function such that the value of f at this point a is equal to 0. So any a that will satisfy this equation. Let's try to find out the domain of this particular function f. That's a rational function. It has certain denominator. We always need to protect denominator not to become 0. So we want to answer the question when 3x minus 5 is 0. Well, it is when x is equal 5/3. So if x is 5/3 and I try to plug t into the expression, the denominator of this expression will become 0, and since we can't divide by 0, we are unable to evaluate function value at the point 5/3. Therefore, 5/3 has to be excluded from the domain. Meaning that the domain of f is all real numbers, but not 5/3. Let's look at the second function, function g. What would be the domain? There's a couple things to protect. We have radicands under the radical sign. The radicands must be bigger or equal 0. That means x must be bigger or equal 0 because of the radicand in the numerator. Also, the radicand in the denominator must be bigger or equal 0. However, we are not taking equal because of the denominator. So overall, it has to be strongly larger than 0, not because of the radicand, but because of the denominator, which is not equal to 0. Now, this condition is already solved, and to solve that condition, bring the x over. X's must be smaller than 3. So we have two things. X is bigger or equal 0, and also x is smaller than 3, meaning that the domain of g function starts from 0 and goes up to 3 without 3. We can mark it on the number line. X's are larger than 0, that means this way, and also smaller than 3. So x's are everywhere in between. Two more examples. What would be domain of the function h? Again, we need to protect the radicand. So the condition to check is 9 minus x squared must be bigger or equal 0. And now we need to solve this inequality. So bringing the x squared to the other side, we have this smaller equal 9. And then applying square root to both sides, we end up with 3, bigger equal, and square root of x squared is actually absolute value of x. So now let's recall how do we solve absolute value inequalities. We're looking for numbers that are not larger than 3 steps from 0. It doesn't matter which way. So if we try to draw it on the number line, x's that are smaller equal 3. Starting from 0, I can go up to 3 steps to the right or up to 3 steps to the left, meaning everything from -3 until 3 with the endpoints. So now we're ready to give the final answer for the domain of h, which is anything from -3 to 3. And finally, the p function, this is piecewise defined function. Since both pieces are really polynomials and each polynomial has domain all real numbers, we simply need to follow the sections of the domain that the function is defined in. So 1 to 3, and 3 is connected with the next section from 3 to 10. Therefore, the overall domain of P is from 1 to 10 inclusive. In the next problem, we are asked to find all a values satisfying the equation that f of a is 5 if we know that f function is defined as absolute value of x minus 3. So what does this really mean? Well, f of a is 5. Therefore, if x is a, plug it in a to the equation, we end up f of a equals a minus 3. But f of a is equal to 5. So we really need to solve absolute value equation a minus 3 equals 5. In order to do that, we need to drop absolute value sign and split this equation into two possible cases. Either a minus 3 is equal to 5 or a minus 3 is equal to -5. In the first case, a equals 8. In the second one, a equals -5 plus 3 is -2. So find all a values satisfying this equation. Well, those a values are -2 or 8. This time we're asked to find all zeros of the specified function. Well, that means what kind of x will give me the value 0. So if we assume that f of x is 0, we really need to solve equation of this kind. X squared minus x minus 30 is equal to 0. A polynomial equation like that we are solving by factoring. And here the factoring is not too difficult. The product is 30, the difference is 1, so it must be 6 and 5. 6 and 5. And the larger number takes the middle sign, so it's -6 plus 5. Since this is equal to 0, so we have either x is 6 or x is -5. Those are the two possible roots of function f. And we could easily graph this function to figure out how this looks like. Since the roots are 6 and -5, we can already plot it. Let's say 6 is approximately here, -5 approximately there. And we know that this is parabola. Since the leading coefficient is positive, this parabola has arms up. So it looks somehow like this. And those are our zeros of the function. So f of x here and x there. The other important features of a function aside of domain and range and its zeros are connected with the behavior of the function. For example, if the function is rising from the left to the right, we are talking about function being increasing on certain interval. If the function is falling down from the left to the right on some interval, we are talking about function being decreasing. Or if the function constantly assumes the same value, then we are talking about a constant function. Formal definition of increasing, decreasing, or a constant function is as follows. Assume that I is an interval in the domain of the function, so certain interval. For example, here I have certain interval I. And I will observe the behavior of this function within this interval. So we're saying that function is increasing on our interval I, if and only if I choose 2 points, A and B, inside this interval, any 2 points, such that A is smaller than B, then when I look at values of those points, f of A, which is here, and f of b, which is somewhere there, then f of b will be larger than f of a. So f of a is smaller than f of b for every choice ab from the interval such that a is below the b. Similarly, a function is decreasing on certain interval I. Again, this would be my interval I. So a function is decreasing on this interval if and only if, for any choice of a and b from the interval I know that the value of f of a is larger than the value of f of b. So here it is. F is decreasing on interval I if and only if f of a is larger than f of b for every choice of a and b from the interval in increasing order. Finally, f is constant on certain interval I if and only if the values of f at a and b are exactly equal for any choice of a and b from the interval. Now, a function that is always increasing or always decreasing in its domain, it's called a monotonic function. Another important feature of a function is a function that is one-to-one. Those are functions that will have each particular value y assigned to only one input x, which means that they will satisfy horizontal line test. What is a horizontal line test? Well, it's very similar to the vertical line test that checks for being a function at all, but now we are checking for being one-to-one. So if any horizontal line intersects the graph of a function at most once, then the function is one-to-one. For example, these two graphs are one-to-one functions because if I put any horizontal line, no matter where, this horizontal line will cross the graph only once. So we don't have the same value assigned to different x's. That wasn't the case in the previous example of parabola. We can notice that a horizontal line passes through the graph twice. So this is not one-to-one function. It's still a function, but not one-to-one. So, since monotonic function is always increasing or always decreasing, it will never come back to the same value that was already used, then any monotonic function is also one-to-one. A monotonic function is one-to-one. For the next two graphs of functions, we want to find out if those graphs represent one-to-one or monotonic functions. Also, we would like to state all possible intervals in which the function either increases or decreases or remains constant. So look at the first example of this function. It's always increasing. So if it's always increasing, that means it's monotonic. It's also one-to-one, and the monotonic is one-to-one. And we know that there is only one interval, and in this interval the function is always increasing. So increasing on, assuming that the line proceeds farther, it's on all real numbers in the entire domain. Let's look at the second example. In both of these examples we assume that 1 square represents 1. So that's 1 here. This function is not monotonic and it's definitely not one-to-one because first it rises, then falls, then rises, and then falls again. So it is neither monotonic nor one-to-one. Why it's not one-to-one? Well, we could draw a horizontal line and we can see that this line passes through the graph many times, particularly 4 times. So it's not one-to-one. Now let's list intervals on which the function is increasing. Increasing on we can highlight the intervals on the x-axis for which the function actually increases. It does increase from here to there. So it starts from -infinity and goes until -2. That's our first interval, -infinity up to -2. We can include the endpoint. That's the tip of the hill. What else? Well, next the graph decreases. Then looks like between 1 and 2 it's constant, and then increases again from 2 to 4. So the yellow segments are the intervals on which the function is increasing. So the second interval goes from 2 up to 4, square brackets. This is 2, this is 4. And now the function is decreasing on the remaining intervals. So let's highlight the decreasing intervals in green. It will be from here to there and from here on to the infinity. So we can record the function is decreasing on the interval, and again we can include the endpoints -2 till 1 and also comma from 4 to infinity. Finally, the function is constant on the interval from 1 to 2. This section also contains some applications. Let's look at the following example. Water is flowing into a conical drinking cup with an altitude of 4 inches and radius of 2 inches. So here we have a diagram to help ourselves. 4 inches is the altitude from here to there, and the radius of the cup is 2 inches. Now we need to write the radius r of the surface of the water as a function of its depth h. So r is the radius of the surface of the water, meaning r is really from here to there. And the depth of the water is h, that means is this piece. Okay, how can we express r in terms of h? Well, we are going to look at similar triangles, the red triangle and the blue triangle. Corresponding sides of similar triangles are preserved. Therefore, we can compare r to 2 is the same as h to 4. r over 2 is the same as h over 4. So, r equals, when we multiply by 2 and reduce with the 4, it will be just 1/2 h. And the second part of this question is to write the volume V of the water as a function of its depth h. So volume V, volume of a cone, will be 1/3 area of the base, which is pi r square, times height, which is h. Now this needs to be as a function of depth only, so I need to replace r in terms of h. So here we're taking advantage of the previous question. R is already expressed in terms of h. We're going to plug it in instead of r to our function. So V would be 1/3 pi, and then it's h over 2 squared times h. And after simplifying, 2 squared is 4 times 3 will be 12. So we can write numerical coefficient pi over 12, and then it's h squared times h is h cubed. So that will be the function of h that describes the volume of water in terms of height. In the next example, we have a triangle bounded by x and y axis, and the line segment passing through the point 2, 2. But obviously this line segment doesn't have to be as on the diagram. It could be positioned somehow like this, or maybe somehow like that. So this blue line is just one instance of such segment. What we need to do is to find the area of the triangle as a function of x. So where's the distance x on this diagram? Well, the line segment crosses the x-axis at the point with coordinates x and 0. Therefore, this segment is of the length x. we need to find the area in terms of x. What is area of a triangle? Well, it's half of the base, which in this case is x, times height, which in this case is y. This is the y. So it is a function of two variables, but we want to give a function of one variable, just x. So what we really need to do is to express y in terms of x. How can we do that? We have this point that we should take advantage of. If we draw, for example, another triangle by projecting point P onto x-axis and consider this red triangle and the blue triangle as two similar triangles, then the ratios of corresponding sides of those triangles will be preserved. What do we know about the sides? We know the sides of blue triangle as x and y, and the expressions for the sides of the red triangle can be developed by using the fact that this point has coordinates 2, 2. So this distance corresponds to second coordinate of point P. Therefore, it's equal to 2. That distance, however, from here to there, we can express by using the fact that the overall distance from 0 to x is x, and then we subtract 2, which is that part. So we subtract 2. Therefore, we have x minus 2 to represent the distance from 2 to b. Okay, so we're ready to state proportion by using similar triangles. For example, y over 2, this over this, is the same as this over that, which means x over x minus 2. And this proportion we can solve for y. Y will be multiplied by 2 times x over x minus 2. So now we're ready to finish our function. It is 1/2 x, and instead of y, we have this expression times 2x over x minus 2 equals, after simplifying, the 2 is gone, and we can write just x squared over x minus 2. So the area is expressed in terms of x only, and it is a rational function, x squared over x minus 2. What is the domain of the above function? Well, generally the domain can be anything except for such values of x that will make denominator 0. So the domain of this area function would be all real numbers but not 2, because 2 would make denominator 0. And here we have the last example. A man in a rowboat that is 2 miles from the nearest point A on a shoreline. Here's the boat, 2 miles from the shoreline. Wishes to reach a house located at a point B that is 6 miles farther down the shoreline. So from point A, 6 miles forward, it's point B. He plans to row to a point P, to a certain point on the shoreline between the point A, that is at the shortest distance, and point B, that represents his house. So point P is between A and B, and it's x miles from the house. We know that the distance from B to P is x. And then he will walk the remainder of the distance. So he rows this way, and then he walks x miles. Suppose he can row at a rate 3 miles per hour and can walk at a rate 5 miles per hour. If t is the total time required to reach the house, express t as a function of x. Okay, so the t is the total time. This time is really the time needed to cover the distance from the boat to point P. Let's call the location of the boat O. So t is the time from O to P, and then we need to add the time needed to cover the distance from P to B. We also know the relation between rate time and the distance. So the t O to P, time, is distance over rate. So the distance OP we need to divide by the rate 3 miles per hour. Similarly, TPB is the distance PB over the rate, which is 5 miles per hour. Okay, and PB is the same as x. So the expression for the second time is already in terms of x over 5. Now the only thing that we still need to do is to express OP, this distance, in terms of x. Well, how can we do that? On this diagram, we can notice that if we look at the triangle OAP, this is a right angle triangle. How do we know it? Because distance of the boat from the shoreline is the distance measured on the perpendicular segment to the shoreline, and this is given to be 2. Now, if we would know the distance AP, then we could find out the distance OP by using Pythagorean equation. Therefore, our goal would be to find out the formula for the distance AP. Since we know that AB is 6 and PB is x, then the distance AP can be seen as 6 minus x. Okay, let's record this fact. Distance AP equals 6 minus x. So we can set up the Pythagorean equation stating that OP squared equals 2 squared, which is 4, plus AP squared, which is 6 minus x squared. Therefore, OP by itself is square root of these two quantities. So it's square root of 4 plus, and we can actually unfold this bracket by applying perfect square formula. So we have 36 minus double the product is 12x plus x squared, which could be written as square root of 40 minus 12x plus x squared. Okay, now we are ready to finish the question. The t, capital T, is equal time for OP, but OP is this much. So let's write it down. Square root of 40 minus 12x plus x squared, everything over 3, plus the second time for walking, which is just x over 5. And as you see, this is our final function of x. So knowing the distance from the house to the point of his landing, he can actually calculate the overall time of the trip from the present point till his house. And being able to write down the formulas for appropriate function in respect to the given variable is quite important for calculus when you may be asked to minimize the time. That means to find out a point that will save him the most time for the trip.